Hello there, I'm Mr. Math Guy, and today we're going to be taking a look at a 10-minute video on circles and chords. So let's take a look at a circle, just to review what a circle and a chord even is. A circle, by definition, is all the points equidistant from a given point. So the given point is A, which is also called the center. All the points that are equidistant from that, and so that would be all the ones on the outside here. And if you connected all those points together, it would give you the circle. So that's the definition of a circle. And we always name circles by their center point. So this would be circle A. Circle A. Now, a chord is a segment that has both endpoints on the outside of the circle. So you can see I have a chord drawn here, a chord BD. Now, you can see that this is a chord. You could have a diameter that actually goes through the center. That's actually a chord. A diameter is a special type of chord. But a chord, nonetheless, is a segment with both endpoints on the edge of the circle. All right, let's take a look at a definition that we have here, one called congruent circles. It's a pretty easy definition. Congruent circles are circles whose radii are congruent. So I have these two circles down here at the bottom. We'll call it circle A, and we'll call this one circle B at the center point. If these radii, let's say this is 3 units and this one's 3 units, if the radii are the same in the two circles, then the two circles are said to be congruent circles. Now let's take a look at a postulate here, the chord postulate. It says, if a line intersects the interior of a circle, then it contains a chord of the circle. So we have an orange line here, and this orange line intersects the interior of the circle, so the chord postulate simply says, then part of this line contains the chord. And you can see from right here, the edge of the circle, the end point there, and to the end point right there, that is a chord. All right. So if a line intersects the interior of a circle, then the line, then it contains a chord of the circle. It's a pretty easy postulate to understand. Let's take a look at a couple of theorems here and explain them. We will not prove them here in this video, all right, although they have been proven, but we will at least look at them and explain them. So the first theorem that we have is, in a circle, if a radius is perpendicular to a chord of a circle, then it bisects the chord. All right, so let me try to draw a circle the best I can here. All right, if we have this circle, sorry, it's not very good, and we have a radius. Remember, radius is a segment from the center to the circle. If it is perpendicular to a chord, so if I have a chord, let's say, going here to here, and perpendicular means these things bisect at a right angle, all right, or form a right angle. If this is the case, if a radius is perpendicular to a chord, then what the radius actually does is bisects the chord. That means it cuts the chord into two equal parts. So if this chord, let's just say, were 10 units, all right, long, 10 inches, 10 centimeters, or whatever, then if this radius is perpendicular to the chord, then that each one of these parts, this part and this part, then would be congruent, and both of them would be 5. So let's just look at a quick example. Here I have a diagram of a circle in which I have a radius, and I have a chord, and I have a chord that is 16 units long, and you can see that the radius and the chord are perpendicular to each other. So then, what would be the length of each part? Well, according to the theorem, the radius bisects this chord, so this part would be 8, and this part would also be 8, just from here to here, all right? From the edge to this place of intersection. So it cuts it in half, essentially. Let's take a look at another theorem that we have. This theorem says, in a circle, or in congruent circles, if two chords are the same distance from the center, the chords are congruent. All right, so let's take a look at a picture of this and explain it. We're not going to prove it, just to explain it. Alright, looking at the illustration, I did the two congruent circles. Now, if two chords are the same distance from the center, so we take a look at the center and we go straight over to it perpendicularly. So if this measure from here to here, alright, if that measure is 4, and let's say from here to here, if that measure is 4 also, they're the same distance from the center, then the two chords are congruent. Then if one chord is 18, then the other one is 18. All right. So if they're the same distance from the center in congruent circles or in the same circle, then the chords are congruent. Let's take a look at a third theorem. A third theorem says in a circle or in congruent circles, if two chords are congruent, then they are the same distance from the center. This one looks a lot like the previous theorem. The previous theorem stated in a circle or in congruent circles, if two chords are the same distance from the center, then they're congruent. What this is the converse. This is the converse of the previous theorem. So looking at our figure here, just using the one circle, if I know that two chords are congruent, so I know that, let's say, chord A, B, and chord C, D are congruent. If I know that they're congruent, let's say they're both 20 millimeters long each, then I know the distance from the chord to the center, right here to here, that distance would be the same from here to here. Right? So it's the converse of the previous theorem. If two chords are congruent, then they are equidistant from the center. So let's take a look at maybe some questions that we might see from figures such as this. If I have a circle and I want to name this circle, well, this circle would be called circle P. And the way that we would denote this, we would say this would be circle P. You always name it by the center. Now, if I wanted to name a chord from this, there's two given here, but one only with letters. I would have chord RS. And if I wanted to name an arc is the distance, for example, from one endpoint going around the out, then this would be arc RS, and that's the symbol for arc. All right, so you have a center P, a chord RS, and then there is an arc RS. Now there are some other arcs. I just didn't label the diameter that we have here. A diameter is also a special type of chord, but you could have other arcs and another chord there for what I have drawn. Let's take a look at a problem that we may encounter with chords and circles. Let's say I have this circle here, this illustration, and let's say that I know that AG is congruent to AC. So the distance from the center to this chord and the distance from the center to this chord are equal. AG is congruent to AC, so the distances are equal, they're congruent. And let's say that I know that BE, the chord, is 12. Well, then what is the length of the other chord? Well, since the distances are the same, the chord length would be the same. So IF would simply be 12 as well. Let's take a look at one that might be a little bit more difficult. This time, let's say BE and IF are congruent. So I know that the chords are congruent. And then I know that BC, so this part is 4. And I know that AB, and it's not given in a line, but we can make it AB is 7. Then what is AG from here to here? What's this? Well, the distance from A to G is going to be the same as the distance from A to C, since we know the chords are the same length. So what we need to do then is figure out, and this will be a right triangle, what that bottom side is. So by using Pythagorean theorem, 4 squared plus b squared equals 7 squared. We have 16 plus b squared equals 49. Subtract 16 from both sides, and we get b squared is equal to 33. Take the square root of both sides, and then that b would be the square root of 33. So AG would be the square root of 33 units. I hope this helped you learn about circles and chords. Thank you for watching. God bless.